Hi there, welcome back to the formulaic approach. Now in this video we are going to be talking about physical quantities and primarily we'll be discussing dimension analysis. Now you see, I'm going to take it from the scratch and build it up. So if you already know the basic things, you can forward the video because I'm going to solve 100 level physics 101 exam questions here. All right, but I will not be naming them, okay? But you will see when you see the advanced questions, so of course you can already relate to them if you are in that level, okay? But this video is so that you can understand from the scratch, okay? But you see, one thing is that I've constantly told you before that you need mathematical skills to be able to solve this, to do well in physics altogether. So if you lack these basic skills, now there is a textbook that I got mine today that I want you to also get. You see this textbook, okay, is a very good textbook. It takes things from the scratch. In fact, this is a textbook that I call Teach Yourself Maths. That's why it's called Foundation Mathematics. Okay, it covers most of the tools that you need for physics. And of course, if you are taking maths, if you are taking exams like WAEC, NECO, NAPTEP, GC, JAMB, or UTME, GMAT, CBSE, IGCSE, Olympiad Maths, and AMC, American Mathematics Competition. Now, this textbook covers everything, okay? It goes from, you see, I cannot even overemphasize. That's the truth. That's why I got it. The person who wrote it is even more like a teacher to me. Do you understand? So please, you can reach out to me on this WhatsApp number. I'll send you his number and you reach out to him, okay? So just do well to get the textbook, okay? It's helpful. It's helpful. It covers most of your basic maths and it helps you to go from scratch to advanced level. All right, let's get into the video. So what are physical quantities? So primarily, quantities are what we discuss in physics. Everything in physics is based on quantities. Is that okay? Yeah, majority of the things we discuss in physics. First, physics study the physical nature of matter, right? So if it's physical nature of matter, we use physical quantities. Physical quantities are those things that describe, those quantities that describe matter physically. Is that okay? Those things or those quantities that describe matter physically. That is what physical quantity is. And that's primarily all we discuss in physics. Do you understand? That is mostly what we discuss in physics. The physical nature of matter. So using what physical quantities. All right. So since we know what physical quantities are, what we use to describe the physical nature of matter, now what are the categories of physical quantities? Let's start with that. The categories, or what I call it, classification. The classification of physical quantities. Now, number one is we classify into two first that we call the fundamental and derived quantities. We also call this one base quantity. So fundamental and derived quantities. Now, then we now have the scalar. You must have heard of this like a million times in physics. Scalars and vectors. Or we say scalar quantities and vector quantities. Then of course we have the third one is dimension and dimensionless quantities. Dimensionless. So indeed there are quantities in physics that don't have dimension. So there are quantities that have dimensions, which is our primary focus, and there are quantities that don't have dimensions. So quickly, let's start with the fundamental quantities. Let's quickly just describe them in a jiffy. Then we'll move to the dimension analysis. So what are fundamental or base quantities? Now, these are quantities that we use to define other quantities. Other quantities are based on them. Is that okay? Other quantities are defined by them. So they are used to what? To define other quantities. So it means that any other quantity we have in physics is generated using fundamental quantity. Okay, so it means that fundamental quantity are the base, that's why we call them base quantities. Okay, they are the basis of description of everything about matter. They are the basis of description of matter. Now, how do we now know or identify a particular quantity? We use what we call units to identify quantity. So units are the expressions used to identify what? Expressions for identifying what? Quantities. Quantities. Now, if it is a fundamental quantity, then we'll call the unit for identifying it, we'll call it what? Fundamental unit. So now when I say identifying, how do we identify? It's by what? Measuring. So we say fundamental units are used for measuring what? Fundamental quantities. So that's why we say it. We say units are measured, quantities are measured in units. Quantities are measured in what? Units. Okay, so I said units help us to identify. Let me give you a context. If I say I ran 2, say I ran. Say how far did you run? I just said 2, and you say what is 2? What does 2 mean? I need to put meters or kilometers to let you know that 2 is not just 2, because 2 could be 2 eggs. 2 could be 2 chickens. Can you run 2 chickens? So it has to be kilometers for you to know that we are talking about a quantity known as length or distance. Is that clear? Okay, so, or displacement. So this tells you, this kilometer is the unit that helps us to identify that we are talking about length this time. Is it clear? All right. Now let's quickly talk about now, what about derived quantities? What would derived quantities be? Of course, just like the name implies, derived quantities are the quantities that are defined by what? Defined by what? Fundamental quantities. Let me put FQ. Fundamental quantities. Derived quantities are defined by what? Fundamental quantities. Now, these ones are measured in what? Derived units. Measured in derived units. Okay. Now, what are the examples of fundamental quantities in physics? Now, the fundamental quantities in physics, they are about, I think, just 7. When we list them, you see. Now, I'm going to be listing their units to what they are measured in. Okay. So these are the fundamental quantities in physics that we have. Number 1, I like to start with time. Time is one of the most important aspects in physics. So matter exists in time and space. So if it exists in space, then it means it has what? Mass. Okay, because mass is the quantity of substance in matter that helps it to occupy a particular space. Okay, so it exists in time and space. So, and of course, we have length, because length describes some things about the mass, the physical nature of the mass. So, for example, you see a huge mass. For example, look at this board. You cannot necessarily tell much about the board in terms of how much mass is there. Listen. In terms of how much mass is there, you needed to, what you just see is observe and describe that this thing is long from here to here. It's about 2.5 meters long, about 1.5 meters high, blah, blah, blah. You understand? So those are lengths. Those are things that you just see and you're able to tell. Then, of course, we have temperature. Matter also has temperature, that is the degree of hotness or coldness. Okay, now the degree of hotness or coldness. Another thing about matter that we measure is we also measure. We know we have temperature. We have what again? Luminous intensity. Okay, that is the intensity of how much how radiant a particular thing is. Okay, luminous intensity. We also have number 6. What else am I missing? I've talked about temperature, current. Okay, there's one more. I think there are about 7. Amount of substance. Okay. Amount of substance. Okay. Now, You see, current is the rate of flow of charge. Now, what is the unit of time? The unit and the units. Let's say what are units. How do we measure time? How do you know I'm talking about time? When you hear things like seconds, right? Of course, these are the base units. I'm going to be writing only the base units here. The base units. Or maybe not just base units, units generally. There's a reason why I don't want to talk about base units yet. When we get to dimension analysis, we'll talk about base units. So when you hear seconds, or you hear minutes, or you hear hour, you know I'm talking about time. So hour is not a base unit. Seconds is the base unit for time. Now, mass. When you hear kilograms, right? So that tells you, oh, we're talking about mass. Of course, we hear gram, we hear microgram, milligram, blah, blah, blah. Those are all units of mass. Is that okay? Now, how about temperature? What do you hear? No, length. What do you hear that helps you to know we're talking about length? I mentioned 2 meters the other time, right? So, a kilometer, in which case we are extending the amount of mass of length. So, and of course, then we have temperature. Now, the unit of temperature is. Yes, sir.
Okay. Are you doing
Online.
online?
Yes, sir.
Sorry.
Okay, so the unit of length, we said meter. The unit of temperature, we said is Kelvin. Kelvin. This is symbol. Okay, sorry, this one is seconds. Symbol. Let's use symbol S. Kilograms. Kilograms. We have kg, meter. We have M, and Kelvin. We also have Celsius, okay? Those are other units, but the base unit is Kelvin, which we use symbol K for. Then we have luminous intensity measured in candela, CD, and current is measured in amperes. Amperes, symbol capital A, or ampere. Amount of something is measured in mole, symbol MOL. Okay, so these are the base quantities and base units. They are just 7. 1, 2, 3, 4, 5, 6, 7. They're just 7 in number. Now, so we now know fundamental and derived quantities. Fundamental quantities. How about derived quantities? Derived quantities are the ones that we're going to be analyzing under dimension analysis. They are the ones that we get by simply, walking around these guys, going up and down doing mathematical operations, various mathematical operations and manipulation with these guys. We come up with derived units. Okay, derived units. Now, let's quickly discuss what scalar is. What is a scalar quantity? Scalar quantities are the ones that have magnitude. They have magnitude, no direction. They have magnitude but no direction. While vectors have both magnitude. They have both magnitude and direction. So they have both magnitude and direction. Then, what that means, let me tell you what this means. Scalars have only numerical values that we use to represent them. We don't talk about, they don't have direction. Their direction does not matter. Is that okay? Their direction does not matter. For example, if I say, I usually use this example, difference between distance and displacement. Both of them means how far you have gone. But in context, one is scalar, the other is vector. This is scalar, this guy is vector. Now what is distance? Look at this. A body can easily just go from here to here, to here, to here, to here, back here, come here. So if the body actually travels, if the body actually traveled 2 meters here, traveled another 2 meters here, 1 meter here, 2 meter here, 1 meter here, and if you add up this 5 meters here, okay, let's say here another 1 meter, 1 plus 5, 6 meters here, then came here 1, that is 2, here 3, That's 5 meters back here. So the body went from point A here to point B here. Now leave how I got these distances, just leave that one. But what I want you to know is the difference between distance and displacement. Now, if the body traveled from here, point A to point B, and I ask you how far did it go? You say, now you use distance. There are two ways you can describe it. Either use distance or displacement. He has traveled the distance, total distance is 2 meters plus 2 meters plus 1 meter plus 2 meters plus 1 meter plus 6 meters plus 5 meters. So his total distance is going to be 2, 4, 6, 12, 18. 18 meters. He has traveled 18 meters. But what is displacement? Displacement is just how far from starting point. It means that there's a reference point and there's a direction. So how far has it gone away from starting point? He has only gone this distance, which I call 1 meter, for example. He has only gone 1 meter due, what direction is up? North. Due north of starting point. Due north of A. Is that clear? So he has only traveled 1 meter due north of A, according to if it's displacement you're using to describe. So you see that displacement has to do with direction, has reference to direction. So it means that we cannot describe this displacement except using direction. But distance, without direction, we can describe. It's just the numerical value of how long someone has traveled. Do you understand now? So scalar has magnitude, has size. Vector has no size. Now, I have a video on scalars and vectors. Maybe I'll link in the description for you to understand in case you are battling with it and you don't understand scalars and vectors. All right. Then the next one is dimension and dimensionless quantities. Dimensional quantities are quantities that have units that we can analyze their unit of measurement. Example is area, dimension quantity. They have units. These ones don't have units. Examples of these ones that don't have units are I remember refractive index, for example. Refractive index. The reason why these ones don't have quantity is because the quantity, they are usually ratios of quantities. So ratio of those quantities, of similar quantities, the quantities will cancel each other, their units will cancel each other, and then this one will end up not having any units. So for example, this one now is, refractive index is ratio of sine of angle of incidence over sine of angle of refraction. By the time you cancel the angles, what happens? You have only numerical value, no units. Is that clear? Another one is relative density. Relative density. All these relative guys usually, most of the quantities that you hear relative, they're usually without dimension. Another is relative permittivity. Relative permittivity that we treat in electrostatics. Relative permittivity is just permittivity of free space, permittivity of medium over permittivity of free space. Both units cancel out, and then the other unit, this one does not have dimension. Is that clear? So that's what we call dimensionless quantities. Now let's go to, there are other ones, okay? I've only mentioned 3 here. Now let's go to dimension analysis. Dimension analysis. All right. Now we're going to analyze some basic ones first before we now start treating good questions. So usually, the one skill that you need to understand dimension analysis is simple fraction manipulation. Then also master formula. Any formula I give you now, you master. Okay? So let's start with the very simple one. What is the unit of, how do you analyze area, for example? How do you analyze area? So you must know the formula for area. Now we always analyze based on mass, length, time. Mass, length, and time. Is that clear? Usually also we can include current, I. We can include some equations. That's what I mean. Might involve or include rather current. Some might include temperature. Some might include temperature. Others might include. So that's primarily the ones that you might have come up. But primarily, what we want to try and do is always reduce to MLT. Those are the basic one that we mostly use. They are the ones that come up the most in physics. Is that clear? Other than this one, even current and temperature. So now let's go to our area. What's formula for area? Area is length times breadth, right? So you probably know this now. Length times breadth. What is length? So what you want to try and do, remember, is to reduce this guy to this form. M for mass, L for length, T for time. So now, length, can we simplify length further? No, length is already, you can, now once it has fallen to base quantity or fundamental quantity, you cannot simplify it further. So you leave it that way. So length, can you simplify it to, can we simplify it further? No, length is already length. So we use L here times, how about breadth? Breadth is a type of length, right? So it's also length. Is it clear? Breadth is still length. Length is the basic, length just talk about how far something is. So breadth is also how far. But because it is a shorter how far, that's why we use the name breadth for it, so that you be able to differentiate between length and breadth. Alright, the two sides of the rectangle. So now, what do we have here? Length times length, length squared. And this is the analysis of the quantity area. But in units, we always express, I always advise to express in base units. What will be the base unit? BU for base unit in this case. What will be the base unit? The base unit will be, what do I have here? L squared. What's the unit of length? Meter, right? So M meter, then squared. That will be meter squared. Is it clear? So that's the base unit there. Now let's analyze another very simple one, which is volume. Now what is volume? Volume is length. What's formula for volume? Length of a thing times the breadth of a solid object times the height of the solid object. Make sense? So now we are going to try to reduce these three again as well to this MLT. Now this does not look like length, or does not look like mass, does not look like time. So what does it look like? Look, all of them look like length, breadth is type of length, height another type of length above the ground. Is that clear? So what do we have? Length, length, length occurring thrice, so that we L cube, and this is the analysis. So what will be the basic unit? The basic unit will be meter still for length, but this time cubed, right? So you see it's very different from area. They are going to be very different. All right, let's go. The next one is, let's analyze another one called, let's analyze density. That's usually this is usually the order you see it in your textbook too, okay? So now let's analyze density. You must know the formula for density. The formula for density is mass over volume. Okay, so mass per unit volume, that's what we call it. Now, what is mass? Can we reduce mass further? No, mass is already mass, so we leave it there as mass over, what is volume? You remember we have the simplified volume already. We simplified it to L cube, right? So we bring it here, L cube. Is that clear? Okay, so this becomes, now you should know this, that if I have 1 over anything, it's the same as that thing raised to power minus 1. If I have 1 over 4, for example, I can simplify this as 1 over 2 squared. This becomes 2 squared raised to power minus 1, which becomes 2 raised to power minus 2. By the time this one multiplies this. Is that clear? So what I'm invariably saying is that whenever you bring a number from the denominator, you take it up, you bring a minus. Then someone said, what if that thing has minus from under already? For example, I have 1 over x raised to power minus 2. Once you take it up, x will be raised to power minus first, because of this division, then minus 2. This now becomes x raised to power minus minus 2. Minus times minus plus 2, which is just 2. So if the thing already has minus under, when you bring it up, it will become minus minus. That will be positive. Okay? So the basic idea I just showed you, or tried to show you, is that when you are bringing something from under up, that thing will become negative. Then it will have a carry a negative power. So this becomes m L raised to power minus 3. And this is the answer. So what about the basic units? So the basic unit is going to look like this. Unit of mass, kg. So write that, kg. Unit of length, meter. And yes, m raised to the power minus 3. So that is the answer. Like that. As simple as ABC. In fact, it's even simpler than ABC. Now, the next one I like to analyze is speed. Okay? Speed. Now, what is speed? Formula for speed is distance traveled per unit time. Distance over time. Anytime in physics you hear per unit something means divided. Is that clear? Now, can I reduce distance further? Is there a formula for distance? Distance is just length. Is that clear? Distance is simply what? Length. Okay? So over, can I reduce time further? I can't. It's already here. T for time. So I can say time. Remember, this T is time. This one is temperature. Theta is temperature. I was supposed to put it here, right? So it's T, this one M, this one L, this one theta. Luminous intensity I. Current. No, current is I, sorry. Luminous intensity, let's leave that. Amount of this, amount of substance, let's leave that too. So if I say, so this now length. Length has been simplified to L, so we have L over time is time, so we have this. So this becomes, remember, we have to take it up to write it in this format. It becomes LT raised to the power what? Minus 1, because this T is coming from under, right? So the base unit will now be what? The base unit will be meter for length, then set time is what? Seconds, raised to the power minus 1. So this is all called meters per second. Another way we write things like this is, another way we write this one is kg per meter cube. Is that clear? So this one too what? Meter per second. That slash means per. Now let's go to the next one. Let's try to analyze velocity. Now you know that. Now what is velocity? Velocity is displacement traveled per unit of time. Displacement per unit time. Now what is displacement? Now displacement is basically length also. If you remember the analogy I did, the description, this thing I gave you the other time, explanation I gave you the other time, it was still a length that we calculated upward, right? To see the position of that guy. So that is still going to be length over what? Time. Okay, so that becomes L over T. Still what? The same as this guy. That was raised by minus 1. So that tells you that this guy, mathematically speaking, velocity and speed are the same. But why do they have different names? Because they are actually inherently different. Speed is scalar. So speed just refers to how fast something is traveling. Velocity refers to how fast something is traveling in a given direction. Is that clear? So velocity is vector, V for vector. Speed, S for scalar. Is that clear? Is that clear, rather? That's number 5. Let's go to number 6. Let's try to analyze the next one. Let's try to analyze acceleration. This is just going by level of complexity, okay? Now I'm choosing to analyze acceleration. What's formula for acceleration? Acceleration is given by change in velocity over time. So primarily we are saying it is velocity over time, or velocity per time. Okay, rate of change in velocity. Okay, this also means rate of change of distance. Exactly. Now this one, time rate of change of velocity. Remember we have analyzed velocity already, right? What did velocity give us? Velocity give us length. I want to just write in full, okay? Length over time. Henceforth, I will stop writing in full, okay? Length over time, that's velocity. Over, this big over is this one here. Is this one here. So over this time now. So this now becomes length over time divided by time. Make sense? This becomes length over time times division of change to times. Remember that, right? And this one will flip over. We have 1 over t. This becomes L over t times t, t squared, right? And this becomes LT. Now remember, we must bring this guy up, right? We like to write it that way. Okay, we don't like to write it in fraction or write it like this. So when we bring this guy up, it becomes negative power, right? Or is power minus 2. If you are thinking the minus just appeared, no, just follow what I told you. I told you that if anything is under and is coming up, it will be raised to power minus 1. It becomes LT This t was squared before, so now raised to the power minus 1. Minus 1 times 2 to now give you L3 raised to the power minus 2. So that's how that transformed. But easily I could just put the minus directly. That's why I did not go through this step. So now let's analyze another one. So what you will do for me now is you can pause the video and analyze force for me. The formula for force is mass times acceleration. Mass times acceleration. So I believe that you should have done that. Now let's do it together. That's number 8 or something, number 7. Now what is force? Formula for force is mass times acceleration. So already mass is fundamental and is already there. So we leave that as that. This becomes m times, what is acceleration? Acceleration is what? Velocity over time that we did the other time, right? So usually, you can just import your answer for acceleration. You can import it here, okay? Which is what I will do next time. So it becomes m times velocity is length over time, then divided by time again. So this becomes what? ml, that's this, over t squared. Now let me teach you a trick here. Next time when you have something like this, what you have is L over T. This is dividing a fraction by a whole number. Dividing a fraction, I repeat, by a whole number. When you do that, just bring the denominator of the fraction, bring it down. It becomes L over T squared. But if you are dividing a whole number by a fraction, for example, it will be T divided by L over T. Dividing a whole number by a fraction. What you do in this one is, this denominator here will come up to become T squared over L. Is it clear? And that's the trick. So here, I simply brought this guy down and then it became this. So our formula for force therefore our dimension for force becomes what? ml, then T is under, it comes up and becomes minus 2. Is it clear? We didn't write the unit for this. We stopped writing unit here. What will be the base unit here? Base unit becomes the same thing here, meter per second. Then here also, base unit. Base unit here becomes what? Meters per second squared. Is it clear? Meters per second squared. Or like m/h raised to the power minus 2. Is it clear? So here too, just follow what you have here, the quantities you have here. M is kg, L is meter, S and time is second squared, like this. Alright, per second squared. Now number 8, let's try to analyze, let's analyze pressure. Let me analyze pressure. So what's formula for pressure? Pressure is force over area. I already have area there. Force over area. Now, if pressure is force over area, then we have analyzed force. So easily, I will just import now. But I don't like to import from here. I like to import from here because this is this, right? So I will say that force is already ml over t squared. I already analyzed that. Then times. Now you know that this thing means force. This thing I can write it as force times 1 over area is the same as force over area, isn't it? Force times 1 force. This is like force over 1. Area times 1 is area. So is it clear? So this thing is the same as saying ml over t squared times 1 over area. Remember that area is length times length, or length squared, isn't it? So from there, L can cancel L. So I can have m times 1, m over t squared times L, that is LT squared. In this case, therefore, we have m, then L. Now, L will be raised to power minus 1 here, and t will be raised to power minus 2. T will be raised to power minus 2. Sir. Now let's continue. We'll analyze Another one, okay, what will be the base unit for this? The base unit will look like this. Mass, unit of mass, kg. Unit of length, m. Then we put minus 1. Then time, seconds. You put raised to power minus 2. And that is the answer there. The next one, number 9, is, so we have pressure. The next one is, let's analyze work done. Now, what's the formula for work done? It is force times distance. Force times distance, or force times displacement. Force times distance, primarily. So what is force? What is force? The unit of force we have analyzed to be ml, the dimension rather, ml to the power ml over t squared. So times distance now is, what's distance? L, right? I showed you here. Distance is the same as length. So that is L over 1. So invariably we are saying that this is ml squared over t squared. So this therefore becomes ml squared t raised to power minus 2. Check, you see that they are not the same, right? So this will be this thing. Then let's talk about the base unit. What will be the base unit? The base unit will look like this. kg meter squared per second squared, or s raised to power minus 2. Is it clear? So that is work done. Now let's go to the next one, which is, let's analyze bigger concepts. Let's analyze inertia, moment of inertia. So moment of inertia, first let's analyze moment. And what's formula for moment? We have moment of mass. So if it's moment of mass, it's simply mass times distance. If it's moment of force, it will be force times distance. So moment of force, we have the same dimension as this, as work done, right? Moment of mass, we have what? Mass, which is m, times distance. What's distance? L, right? ml. Okay, so this becomes ml. Is that clear? All right. Now, how about moment of inertia? Moment of inertia. Moment of inertia, I, is given by the formula. That will be the product of the mass of the body and the square of the radius about its axis of rotation. So that will be mr squared. Now, radius is also a type of distance, right? Distance from the center to the circumference. That's what radius is. So that is mass times radius times radius. Does this make sense? Now I told you radius is a type of length, so we have mass times length times length. So this becomes ml squared. Is it clear? ml squared. Now how about torque? Torque is also force times radius. So in that one, it's also going to give you this. Torque is also, so this guy, moment of force, torque, they're going to have the same formula. Is that clear? All right. Another one is impulse. Let's try to analyze impulse. Impulse. And impulse is force times time. Force times time. Now what's formula for force? We already know that it is ml over t squared times t. Make sense? So you can already see that t squared here is t times t, right? So one of the t's go, and then we have ml over t, which becomes ml t raised to the power minus 1. And that is that. Now the next one is, see, I'm no longer numbering. Let's analyze stress. Stress. Now what is stress? Stress is pressure, right? Stress is force over area as well. Force over area. So it's going to have the same unit as pressure. So the unit is also going to be it's going to have the same quantity rather, the same analysis, the same dimension as pressure. What is pressure? Pressure is ml raised by minus 1 raised by minus 2. So that is that. Now, they all have their individual units, okay? There are other units. So for example, this one, the unit of stress is the unit of pressure. That one is the same. But unit of pressure, for example, and so what are the units of pressure? The standard SI units of pressure include pascals. Pascal, we can use Pascal. We can use these other guys: millimeter mercury, horse, pressure. ATM, horsepower is power. ATM, millimeter mercury, 760 mmHg. That is 1 ATM, which is 1 times 10 raised to the power 5 pascals. So 1 times 10 raised to the power 5 pascals is 1 ATM. Okay, that's standard pressure, and in ATM, and in pressure in mmHg is 760 mmHg. All right, so that's that. So now let's now do some bigger ones. Let's try to analyze Young's modulus, coefficient of elasticity. So we call it coefficient of elasticity, or we simply call it Young's modulus. So when students see Young's modulus, they tend to remember it. If they see coefficient of elasticity, they might say, what is that? So it's simply Young's modulus. One other thing I have said to analyze is strain. And what is strain? Strain is simply extension over length. Now extension is in meter, is a length. Length is the length. So what do you see? It is dimensionless. Yes, sir. Strain is also what? Dimensionless, like those other guys that we saw, relative this, relative that. So Young's modulus is going to be what? Stress, tensile or compressive stress over tensile and compressive strain. Stress over strain. And we know that strain is dimensionless. So it means that the unit of this guy, Young's modulus, is going to be what? The unit of stress, which is what? M raised by minus 1, T raised by minus 2. So Young's modulus is going to have the same unit, but they are not the same. Okay, mathematically speaking, their unit is going to be the same. Stress and Young's modulus and pressure. Is it clear? Now let's do coefficient of viscosity. Now, because I'll be doing bigger questions now, I like to clean the whole board. I want to do coefficient of viscosity. And the formula for so let's talk about coefficient of viscosity, please. Coefficient of viscosity. Coefficient of viscosity. So is that guy in physics that we write like this? Do you remember? Okay. So it's the formula is I think that's force divided by area times V over L. We call that the velocity gradient. That's what we call it. Velocity gradient. Okay, so we should have not seen other gradient, but let's just continue. So N equal to force over what is area? Length times length. Sorry, let's start analysis. What is force? Force is MA, right? More like ML over T squared. I've told you that before. We've done that. Area is going to be length times length. That's length squared times what is velocity gradient? Velocity gradient is V over L, but velocity per unit length. So that will be V over L. So from here, this becomes ml. I told you when you are dividing a fraction, this guy can come down and become over t squared times 1 over l squared. You know this thing here is 1 over this. Then times, now when you are dividing by a fraction, this one can go up. I've told you that before. L over v. Is it clear now? So from there, you can already say length will cancel one of this to remain 1, right? To remain 1 here. This length will cancel one of these also, right? But velocity is not done, right? Velocity is supposed to be, we have not broken down velocity, so we have to still break it down further. Okay, so let's work with what we have left here. We have m over t squared times, everything on top is 1. Now here we have this guy left, velocity. What's formula for velocity? L over t. L over t. So this t can take care of one of the t's, right? So it will remain 1t here. So our coefficient of viscosity become m over t L. Okay? So, or LT. So that becomes m L raised to the power minus 1, t raised to the power minus 1. And that is the answer. So what will be the base unit? The base unit will look like this: kg meter per second. This will be the base unit. All right. Now let's deal with electricity. Let's start with voltage, for example. Should we start with voltage? Yes. Voltage. Or we should start with, let's start with voltage. Or resistance, anyone. Let's have potential difference. Potential difference or voltage. What does potential difference mean? Q is equal to, potential difference V is equal to what? Work done per unit of charge brought from infinity to a point. So, if that's the case, then we know that V is equal to, what's this guy? Work done is force times distance, right? So if that's the case, then we know that, over charge. Now charge, recall that current is the rate of flow of charge. So therefore Q is equal to what? IT. Does that make sense? So we can say that IT here. Okay? So from here, therefore, we can say V is equal to force, which is ml over t squared times length again, okay, divided by current, which is I, times time, which is t. Is it clear now? So it's easier to break down charge this way. So therefore V becomes ml over L times L squared over t will come down, becomes t squared times I times t. I've told you that before. Now when you are dividing a fraction by a whole number, this one will come down, okay? So, is there anything cutting? No. So we have voltage equal to ml squared. We usually write I before t, so I want to write I is under, so it will raise to the power minus 1. Anyone under, raise to the power minus. Then t times t squared times t, that's t cubed. We have t to the negative 3. And this will be the unit, the dimension rather, for voltage. Now what will be the base unit? Kilograms, length, meters squared, current, per ampere, time, seconds cubed. Is that clear? Good. Now the next one I want to deal with is, I like us to deal with this guy, capacitance or resistance. Let's try resistance. So what is the formula for resistance? You probably should already know that from the formula Ohm's law, that V equal to IR. From here we can say that resistance equal to what? V over I, right? But I don't want to use this all alone. There's another formula we have for resistance, which is, remember that resistance of the resistor is directly proportional to the length of the resistor, or inverse proportional to the area. So we have this formula also. So you can use this to analyze it as well. Use use this. Well, you will not get the same unit from what I'm looking at. But so let's use this. So from here, I already have voltage to be this. So with this voltage, my voltage gave me m L squared over T cubed times I. So then this multiplied by, this thing means V over 1 times 1 over current, right? So from here also, this times 1 over current. So it means that my resistance becomes ML squared current squared T raised to the power minus 3. Is this clear? Good. Now, what with this base unit? Base unit becomes kg meters squared A squared seconds raised to the power minus 3. Is it clear? Now keep in mind that they are not the same. Are you looking at that? Now the next one, let's try capacitance before we start trying constants. We'll try capacitance before we do constants. So we won't do this constant, that's resistivity. So now what is capacitance? The capacitance of a capacitor is going to be Q over V. Quantity of charge stored per voltage of electricity passed into that capacitor. So from there, we can easily say that quantity of charge is going to be IT, from what you already know, so over V. So C therefore becomes IT over, what is V? V, we've gotten it to be M L squared over T cubed I, right? Dot also means multiplication, okay? Let me just put it there. So I told you before that if you are dividing a whole number by a fraction, this whole thing here will come up, right? So C becomes IT multiplied by T cubed I over ML squared, like this. So this therefore becomes I times I squared T to the third over ML squared. So if you want to write this in full, this becomes C equals, M is now down, so it becomes L raised to the power minus 1, L raised to the power minus 2, I is up, so I squared, T times T, I squared, T times T cubed is T to the fourth, please, T to the fourth. So we have T raised to the power 4. Is that clear? Then what will be the base unit? Base unit becomes per kg per meter squared ampere squared seconds quadrupled. This will be the base unit. So that is that for those guys. Now let's analyze some constants. For example, let's analyze this constant here. We should be able to do it here. I want to analyze this constant here. This guy's resistivity. Make it subject to formula. Rho becomes RA over L. Make sense? So therefore, rho, remember that rho is resistivity. Resistivity is the measure of how much a material does not permit current flow, the flow of current. That is how much is the measure of how much a material is unwilling to conduct electricity. The measure of how much the material is unwilling. All right, sir. Yes, sir. So, what is resistivity? Resistance, we calculated that here to be, we got that here to be ml. So, let me take it from here. No, let's take it here. So, that will be ml squared T ml squared I squared. This one means over T cubed, right? Over T cubed. So these are times area. What is area? Length times length. Now, all of this multiplied by 1 over L, because this means RA times 1 over L, right? So all of these multiplied by 1 over L. So L will take care of one L, such that resistivity now becomes ml cubed. We have three L's now. So that becomes ml cubed, I squared per seconds, per cubic seconds. So that becomes kg meter cubed a squared per second cubed. And this will be the unit of resistivity. Now what you should do for me is, now let me do one more. There's one constant, this G, in Newton's law of Newton's gravitational law. So the Newton's gravitational constant, it says Gm, the law says that the force of attraction between two masses, m1, m2, is directly proportional to the square of the product of the masses, and inversely proportional to the product of the masses, and inversely proportional to the square of the distance between them. So what will G be here? G will become Fr squared over m1, m2. So let's take that as m squared. G if the masses are the same. So G therefore becomes, what is force? Unit of force, and dimension of force. I'm using this place. ml t raised to the power 2, right? That's force. Then times distance is r squared is distance squared. That is L squared. Make sense? Now, this, from what I've been doing, is just times 1 over m squared, right? So times 1 over m squared. So 1m here will cancel 1m here. Okay, nothing is cancelling again. So G therefore becomes L cubed over mt squared. Our answer becomes m per m raised to the power minus 1, L raised to the power 3, t raised to the power minus 2. So this will be the dimension for Newton's gravitational constant. And from here, you can already see the units. Per kg as kilograms meter cubed, per kg, that's kilograms per 1 meter cubed, second raised to the power minus 2. Now, let's solve A-level questions. So I'm going to write some questions on the board, and then I'll solve them, and you see the way I'm going to solve them. All right, let's attempt these first three questions. It says, the period T of a simple pendulum depends on the mass of the bulb, the length L of the thread, and acceleration due to gravity. Now, you see, this is a very simple question. The first skill you need to know how to use is proportionality. What's that thing called? Variation. Okay, so now, like I said initially, this textbook also even covers basic variation and advanced level variation. So do well to buy it. Okay. All right. My point. The period T of a simple pendulum depends on the mass. Yeah, like I was saying, if you missed what I said, like reach out to me on this number, and I'm going to show you. I'm going to send the number of the writer to you so you can get your copy. You see the volume, very big textbook, but very affordable, and the volume, the content. The content is very, very rich. Okay, and let's just continue. Now the period. Now look at this. You need these two variation scale. If I say something is directly proportional, now if I say, for example, x is directly proportional to y, I'll say x is directly proportional to y like this. If I say establish a mathematical relationship between them, you basically just say that x will be equal to k a constant y. This constant is the condition that makes this relationship to be true. Without the constant, the relationship might not exist, will not exist. Is that okay? So there is always a constant of proportionality. But usually the language is what confuses students. Now, whether they say directly proportional or just proportional, they mean directly proportional. Is that correct? So you have, so if I say inversely proportional, it means x, if I say x is inversely proportional to y, you say x is inversely proportional to y. Is inverse. Okay? Then if you want to write this mathematical equation, it becomes x equal to k times 1 over y, which is k over y. Let me change this thing. So like I said, so that's that. So now let's treat this question. You're going to see how to treat it. It says the period t of a simple pendulum depends on the mass. I hope this is showing well. The period t of a simple pendulum depends on the mass. The period t of a simple pendulum depends on the mass m. So t is proportional to m. That's how to establish the relationship. Is that clear? It's dependent on the mass. So it means that it's proportional to the mass. Then the length. So we can also say that that same period is proportional to the length of the thread, and the acceleration due to gravity. The same guy t is proportional to what? G. Okay. Now use the knowledge of dimension to obtain an expression for period of oscillation. Okay. So what do? Since they said it depends on these three, then I can merge them up together by saying that t is directly proportional to my m, my l, and g. So L here is small l. Okay. All right. So if this be the case, it means that mathematically speaking, t is equal to kmlg. All right. Now, for this equation to be true, m has to be raised to a particular power if you are using dimension analysis. Make sense? L has to be raised to a particular power. I put that as y because it might be different from m. Then g also has to be raised to a particular power for that relationship to actually be true. Is that clear? So we cannot say that this is the exact equation. These powers, there are powers that these guys must carry for us to know what the formula of t is, because that's what we're actually looking for. There are three major uses of dimension analysis, and I was supposed to even give you that. The first use is to check for correctness. I use the mnemonic CRU to remember. The second one is relationship between components of the equation, relationship between quantities, and then we also use it to generate formulas. In relationship is where we use it to generate formula. So this is the relationship between them. Okay, that's what we use it to generate formula. The third one is to find the units, the base units of an equation, of an expression. So those are the three functions of dimension analysis, or uses, or importance. Now, here we can therefore say that t will be equal to, now, what is period? T is period, right? Equal to our constant, is not changing, times, now, m is mass, according to this question. So we'll leave it as m raised to power x. You know what I'm trying to do now? What I'm trying to do is now express these guys in terms of my MLT. Is it clear now? So multiplied by L, length, so it's not changing also, raised to power y. Then multiplied by acceleration due to gravity. So what's acceleration due to gravity? That is acceleration, right? That is LT raised to power minus 2. Do you remember? Then raised to power z. Remember that, raised to power z. Then you now ask me, but master, there is no MLT on this side. So how do we make this? How does the relationship stand? So let me show you. What you will do is now bring M and L that is here. It's only time that we have here. So let's bring M and L here. L becomes M. Now, since there was no M here before, it means M was raised to power 0, because M raised to power 0 is 1. So 1 times T is still T. L was not here before, it means L was raised to power 0. Then T was actually here, T is raised to power 1, equal to K, M to the X, L to the Y. Now here, L to the what? Here, L will be raised to power Z. Makes sense? I like to use dots now as multiplication. Then dot T raised to power minus 2Z. Is it clear? Now what does this tell you? From here, m raised to the power 0, l to the 0, t raised to the power 1 is equal to k m to the x. Now, l, there are two l's here, it becomes l raised to the power y plus z. Remember, multiplication of base in indices means addition of the powers. Then t to the minus 2z. Okay? So from here, we can say that we can equate the terms. Why? Because on this side, we have m here, 1. Here, we have m here. So it means that m raised to the power 0 must be equal to that m raised to the power x. In which case, we cannot cancel. We are not cancelling. I've told you that before in indices. What is happening is that if the bases are the same, then the powers must be the same. X equal to 0. You see that textbook will show you that also. So make sure you buy yours, okay? Make sure you buy yours. It's very affordable. That's the easy thing. That's the interesting thing about it, okay? Just text me on that number. I will send his number to you, and then you reach out to him. So I want you all to be good, have good basic math skill, okay? Because you cannot thrive in physics if you don't know math. That's the truth. That's the truth. I've told you that before. Okay. So x equal to 0. So you see, we've gotten our x. So, but unfortunately, x is never appearing in the rest. So we have to continue our work. So from here, you also see that L raised to the power y plus z, but L raised to the power 0 here. So L raised to the power 0 here should be equal to L raised to the power y plus z. Now what does this tell you? If the power bases are the same, then the powers must be the same. That is, y plus z must be equal to 0. If that be the case, then here y is equal to what? Negative z. Okay? So if y appears somewhere else there, then we can easily solve for it here. But it's not appearing again. So this question is very simple. Okay, so here, y is quite useless because it's not appearing anywhere else. But let's just go on. So from here, I can say that t, therefore, raised to the power 1 will now be equal to this. So t, I'm equating all the parts. T raised to the power 1 will be equal to what? T raised to the power minus 2z. If that be the case, then we know that t at the bases are the same, powers must be the same. So minus 2z should be equal to what? 1. So divide both sides by minus 2 over minus 2, z equal to minus 1 over 2. All right. All right. All right. All right. All right. So if that is the case, we need an expression for y. Because y is minus z, right? So from here we know that. We're supposed to name equations. This will be equation 1. Let's call this equation 2. Okay, so from equation 2 now, from equation 2, this is equation 2, that y is equal to minus z. Now, z is this now, so y will be equal to minus everything here, which is minus half. So y definitely is what? Minus, or plus rather, minus times minus plus half. Okay? Good. So, the question said we should establish a relationship, right? So how do we now establish relationship? Look at what you do here. You go back to the relationship that you began with, which was this. Exactly. So this relationship here, I was supposed to also bring this out. This relationship. So you now say that it is t equal to k multiplied by m raised to the power x. What is x? 0. So that does not appear. That is 1, right? Or you can write it if you want. M raised to the power 0. L raised to the power y. What is y? Y is raised to the power half, right? Y is half. What is z? G is raised to the power z. What is z there? Z is negative half. You see where I'm arranging it now? So therefore, from here we have t equal to k times m, which is 1, is still k. Now, L is raised to the power half. In maths, if you have anything raised to the power half, see, you have, for example, if I say a raised to the power 1 over 3 is the same as the cube root of a. If you don't understand, I will link my video in the description for indices, but you get more knowledge of indices from this textbook. Do well to buy. Just reach out to me. I am going to send you the number. Now, of course, there's also There's also, I laugh because someone is saying that, why does he keep advertising this thing? The truth is, I need you to understand maths. See, I've seen some questions that students ask in physics, and I'm like, did you ever do maths? You see, if you don't understand maths, you can't thrive in physics. All right. So, okay, hey. So I was writing the relationship. So if I now have a raised to power half here, it will be the square root of a. Then I ask, why did I not put 2 here? In maths, we don't need to put 2. For even when we don't put 2, it means the square root. Is that clear? Because the first root of the number is the number. The square root or second root of the number is this. The third root is where we now start putting number. Fourth root, we put 4. Is it clear? That is greater than 2, we'll be putting the number there. So here, this thing means square root of L. Then multiply by negative power means this thing came from under. That is 1 over g raised to power half. What is g raised to power half? It means root g, right? So t therefore becomes k root L over root g. So we can put it together as root L over g. If you have seen my video on simple harmonic motion, I derived this formula for you in full perspective, full derivation. So this formula is actually correct. That k in that video, remember that k is 2 pi. If you have not seen it, I'll link it in the description. So t therefore becomes 2 pi. 2 pi root L over g. And this is very correct. Now let's go to number 2. Number 2 says that, excuse me, that the viscous drag F, drag is a force, the viscous drag F experienced by a spherical bulb of radius R falling through a liquid is proportional to the radius of the bulb, coefficient of viscosity, and terminal velocity. Okay, so we're saying that F is directly proportional to this F4, sorry. Is directly proportional by experienced by this of radius R is directly proportional to the radius of the bulb R dot. So from here, I will not be using all these many this thing. I'll just go one like that. That's proportional to the radius. That's the way you interpret it. Radius, coefficient of viscosity, and the terminal velocity, and velocity v. Is it clear? So from here, therefore, I can say that F will be equal to what? K R. This is we normally write it though. I think the value of K was given. K is 6 pi, but we don't need to use the 6 pi yet. So K R. I've forgotten what this is. I've forgotten. I'm very sorry. V. Coefficient of viscosity. That's sign. Okay, so F becomes K. Okay, so we can eyeball K. You notice that K just kept appearing here and it didn't do anything. So we can eyeball K, but either way, if you still put it, it doesn't affect anything. K times. Now, this is our relationship. This is our relationship that we're going to use at the end. But let's first, simplify these guys. What is R? R is length, right? So it will be R raised to power X. Coefficient of static friction raised to power Y. Coefficient of viscosity raised to power Y. Then velocity raised to power Z. Let's do it this way. Now someone might be asking, what if I put V first and R first? Any way you put it. As far as you arrange your letters X, Y, Z, or any number that you have there, A, B, C, D, any number you have, you get the same answer. In as much as you solve rightly, okay? Now let's analyze force first. Force is ml over t squared. Do you remember? Good. Or ml t raised to power minus 2, right? So this is equal to this relationship we are using rather, not this, because we want to slot in our values. So this becomes k dot radius is length, right? So that is L raised to power x times coefficient of viscosity. Remember we did it. It gave us n L raised to power minus 1, T raised to power minus 1, I think. I think so. Let's just use it. So times velocity. So if I use dot or velocity or times, it's the same. Times velocity, which is meters per second, then raised to power z. Is this clear? So from here, you can therefore say that NL T raised to power minus 2 is equal to K. Now let's open the brackets. L to the x dot M is raised to power 1 here times y. M to the y. L raised to power minus 1 times y. You are distributing the y on everybody. Minus y. T raised to power minus y. Make sense? Dot L, you distribute z too. L to the z, t to the minus 1. Then you now bring guys that are alike together. So m, L, t raised to power minus 2 becomes k. Now, L raised to power x dot L raised to power minus y dot L raised to power z. You bring them together. Then multiplied by m, you're only bringing them close, okay? Multiplied by m raised to power y is the only one there. Then multiplied by t. T raised to power minus y and t raised to power, t raised to power minus 1 times z is t raised to power minus z, okay? T raised to power minus z. Don't forget, oh, please, don't forget. Don't forget. That's the essence of putting that x, y, and z. That's the essence. Is that clear? Now, the next thing we want to do is that we want to solve this. We want to collect this together. That becomes ml raised t raised to power minus 2. Excuse me, please. So this becomes equal to, so we collect L's together, K, just like we did here. L raised to power now. You add up all the powers because multiplication of bases means addition of powers. X plus minus y plus z. Okay, dot m to the y, m is alone. Dot t, you collect t's together, into bracket minus y plus minus z. Is this clear? So from here we can say that we can now begin to equate our coefficient, our quantities. M is alone here, M is alone here. So we say that m raised to power what here? 1 is exactly equal to m raised to power y on this side. Because m raised to power 1 cannot be equal to any other thing apart from m there. Is that clear? So this becomes, shows that if the bases are the same, the powers must be the same. So y equal to 1. So you see we have gotten the value for y now. So any other place where y appears, we can solve. So L now is equal to this L raised to power x plus minus, that's minus y plus z. Make sense? So if the bases are the same, the powers must be the same. This is 1, right? So 1 is equal to x minus y plus z, equation 1. But notice we have gotten the value for y, which is 1. So 1 is equal to x minus 1 plus z. Let's say I come here, it becomes 2, right? 1 plus 1. So 2 equal to x plus z. Okay? So this will now be our equation 2. Alright? I mean, equation 1 did not even change to anything, so let's make it our equation 1. Our equation 1. Alright. So from here, we know that we have now equated t. T raised to power what here? Minus 2 should be equal to t on this side is raised to power what? Is raised to power minus y minus z. So t raised to power minus 2 equal to t raised to power minus y plus z, that kind of thing in bracket. So t and t equal bases, powers must be the same. So we have minus y minus z is equal to minus 2. Recall, we've gotten a value for y. Y is 1. So minus 1 minus z equal to minus 2. Let 1 go there, becomes minus z equals minus 2 plus 1, right? So minus z becomes minus 2 plus 1, that is minus 1. So take z, minus takes care of minus, so that z equal to 1. So I've got a value for z, so we can use it to get a value for z from equation 1. So let me just put that here, that from equation 1, we know that x plus z equal to 2. So x will be equal to, since z is 1, 2 minus z, which is 1, so therefore x equals 1 also. So we'll now write our equation connecting them. So the equation connecting them becomes y, you know this is the equation we said we use. F equals k r raised to power x, I raised by x, coefficient of friction of viscosity raised by y, v raised to power z. So F therefore becomes, what is K? K was given at 6 pi, so it becomes 6 pi. R raised to power, what is value of X? X is 1, so we leave it as 1 here. So R raised to power that. And now, this guy, coefficient of friction is raised to power y. What is y? Y is also equal to 1, right? So we leave it like this. So then velocity is raised to power what? I mean, raised to power z. And what's the formula? What is the value of our z? Z is also 1. So we have v. If you remember the formula, this is the way we normally write it. The F is equal to what? 6 pi r omega rv, sorry. I mean, this guy rv. It's not omega, this guy has his name, I've forgotten it, I'm sorry. This is normally write the formula. So it shows you that we are correct, okay? All right. Then the third one. Now, let me see if I have another question first. No, let's solve the third one. So I want to know if it's the final one I'll solve, or I'll give you one more. But if you need questions, that's the truth, just reach out to me on that number too. Reach out to me for questions, okay? Reach out to me for questions. Then the same distributor also sells one advanced level physics. So, and that advanced level physics also works for both national exams and international exams. So if you need it, I think that one costs about 8,000 naira according to him, or 9,000 naira. But it's very big, and I said very big. Yeah, it's big. The first day I saw it was big. But it's actually all encompassing. Do you understand? It has it treats a lot of things. It's useful for your O level and A level. So also reach out to me. I'll reach out to him for the same book. All right. So I now said that, okay, the third one says the speed of sound in a gas. The speed, let's use V of sound in a gas, is proportional to the pressure P of the gas and its density rho. If the constant of proportionality K is 1, obtain an expression for the speed. So very easily we know that V will be equal to K P rho here. So let's put our powers. It becomes K P to the X, rho to the Y. Alright? So let's now go on to solve. It said to obtain an expression for speed. So we can easily just clean this place now. So we can solve it. So V, velocity is, remember, is L to raised power minus 1, right? Is equal to K. Okay, so it said we should take K as 1. So we don't need to work with it. Pressure is force over area. So force over area, or is by X. Rho is mass density, mass over volume, or M over L cube, or is by Y. So L is by T. I have to first what you want to first do is reduce this one to the lowest, this thing. Reduce this guy to, reduce this guy to the fundamental quantity. So it becomes ml over t squared times l squared. I've showed you this before. All raised to the power x. Then here we have m raised to the power y, or more like m over l cube. I'll just repeat it. All raised to the power y. So from here, I'll have that l t raised to the power minus 1 is equal to m. L takes care of 1l, becomes l raised to the power minus 1, t raised to the power minus 2. Okay, all of them raised to the power x. Then dot m l raised to the power minus 3 all raised to the power y. So from here, we'll do the same thing. Distribute x for everybody. So l t raised to the power minus 1 is equal to m raised to the power x, l raised to the power minus x, t raised to the power minus 2x, when x is distributed for everybody. Dot m raised to the power y, l raised to the power minus 3y. Okay? So we can now compare coefficients now. So that we have here, m is here, right? But it's raised to the power 0. If we just decide to put m. So that m raised to the power 0 here will be equal to, since m appears here, m raised to the power x dot m raised to the power y. That is 0 will be equal to, or more like m raised to the power 0 is equal to m raised to the power addition of powers x plus y. Is it clear now? So that from here we have that 0 is equal to x plus y. This is equation 1. That's equation 1. So this, I'm going to clean this side now from this side, literally. All right, so we'll continue. It says, so we have equation 1 is that x plus y equals 0. This is equation 1. So from here also, we have picked for x, for m, so we can cancel out all our m's. Then l is raised to the power 1. So we have l should be equal to all the l guys collected together. L raised to the power minus x dot l raised to the power minus 3y. So l becomes l raised to the power minus x plus minus, that is minus 3y. So from there, I can, equate the bases. Equation of, if the bases are the same, powers will be the same. So I have minus x, I'm flipping. Minus x minus y equals 1, right? Now, you see, if as a mathematician, I can easily do this. What would I do? I don't need to get to the end before I know what to do. Now, some people will get to the end before knowing what to do. Okay, let me first get to the end. Then you see what I wanted to do here. This is equation 2. So from here, t, for t raised to the power 1, minus 1 rather, l has gone, l's have gone, l's have gone. T raised to the power minus 1 will be equal to t raised to the power minus 2x. For most of your questions, it always ends up that without solving everything, you can get everything by solving or giving values, resolving everything. But there are some that you can use math trick, which means that you need to know math. Okay, it's not even math trick. By the way, that textbook too has a lot of tricks, honestly. Especially if you are taking math Olympiad, you need math tricks. So that's the reason. So in fact, that's one of the reasons why I just get the book. So we have TT, equal powers means equal bases means equal powers. So we have this, it must be the same, divide both sides by minus 2. This takes care of this, minus takes care of minus, so x equal to 1 over 2. Since x is now 1 over 2, I can substitute here, right? So if I substitute, sub for x, substitute 1 over 2 for x in equation 2. What is equation 2? Minus x minus 3y equals 1. So if that's the case, I know that minus 1 over 2 minus 3y is equal to 1. This one goes there, becomes minus 3y equal to 1 plus 1 over 2. Okay? So minus 3y becomes 1 plus half is 1 and a half, which is 3 over 2. So from here I can cross multiply. I have minus 3y multiplies 2 to give 3. Yes, sir. So by the time you cross multiply, you have this. So minus 6y equals 3. Divide both sides by minus 6. And then you have here 1, here 2. So y will be equal to negative half. So y equal to what? Minus half. Now this is what I wanted to show you, that if you had done this from here, say that x will be equal to what? Negative y. Make x subject of formula from here. So x will be equal to negative y. You can come and substitute here that minus x is minus 3y equal to 1. So since x is negative y, it will be minus y minus 3y equals 1. So from here we have plus y minus 3y equals 1. Plus y minus 3y, that's minus 2y equals 1. Divide by minus 2. And then you have y to still be minus 2. You see, it's faster that way. That's what I said you could have done. That was manipulation. But either way, we've gotten our y and we've gotten our x. So what will be the relationship between them? The relationship between them is from where? From here, right? So that relationship, since k is 1, will be equal to p raised to power x. What is x? Half. P raised to power half, rho raised to power y, which is negative half. So you can rewrite as v equal to root p over, because negative means to come from root from under, right? So root rho. So we have root p over rho. So that is the formula. Now, let me write one question on the board. Now, if you need more questions, if you need me to solve more questions, let me know in the comment section. I'm going to attend to those questions. Right now, I'm not tired. I have the strength of God. Do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. And as well, if you need chemistry and physics materials, you can always reach out to me. Like I said, and maths also, please reach out to me and get this one. This particular one, I have tested and trusted. Okay, God bless you. Foundation Maths. That's the name, the name of the textbook. Do well to subscribe to the channel.